Many thanks to the organizer for the opportunity. My name is Nabendu Kumar Khan. I'm a PhD student at Tata Institute of Fundamental Research, Mumbai. Today, my topic is towards more accurate models of Lyman-α forest. This work has been done in collaboration with my PhD supervisor, Girish Kulkarni, and several people listed here. Let me first start with a quick introduction to the Lyman-α forest. So the idea is very simple. You find a bright object at a distance from us. Typically, quasars are a good example for this purpose. And you take a good spectra of these objects using a terrestrial telescope. Due to the expansion of the universe, different frequencies in the spectra of this quasar will encounter neutral hydrogen at different locations along the sightline. And if there is neutral hydrogen, that will cause a Lyman-α absorption feature in the spectra if certain conditions are met. This is an example of Lyman-α forest in a quasar of spectra, which is at redshift 2.77. You can see the continuum spectrum. You can see the continuum spectrum of the quasar, and this is the intrinsic Lyman-α emission line. And bluers of that, you can see a dense network of absorption lines. This is how Lyman-α forest generally looks like. Lyman-α forest can prove very small scales in the order of 100 kiloparsec or so. And at these scales, nonlinear structure growth is important. So one needs cosmological hydrodynamic simulations in order to model Lyman-α forest. Statistics of the Lyman-α forest are measured from observations and compared to numerical simulation results. And in this way, one can infer different cosmological parameters, dark matter mass, and thermal state, etc. An example of the Lyman-α forest statistics is the flux power spectrum, which depends on the structure on a multitude of scales. So here is an example of dark matter mass inference. So Roger et al. Has put a bound on the ultralight axion mass of order of lower bound of order of 2 times 10 to the power minus 20 electron volts using the Lyman-α flux power spectrum measurements, whereas Irsich et al. Put an equivalent bound of lower bound of 4 times 10 to the power minus 21 electron volt. So there is a disagreement in the measurements of the dark matter inference in the literature, which is 5 times. And this disagreement seems to be enhanced with the upcoming improvement in the data, in the error bars in the data from the future large-scale structure surveys like DESI, WMAP, QSO, LSST. So we need improve model of the Lyman-α forest in order to consistently infer the data. And in this work, we have explored the cosmological initial conditions, the accuracy of the cosmological initial conditions, which are used in the Lyman-α forest simulations. So with that, I will first discuss the traditional methods of generating cosmological initial conditions. The cosmological density perturbations are sampled from a Gaussian random field in the Fourier space, and this Gaussian random field is fully specified by a power spectrum, the total matter power spectrum, which you can obtain from the linear perturbation theory. And then you can get these displacements from these fluctuations using the Zeldovich approximation, which is given by this equation. And these displacements in the particle displacements in the Fourier space are transformed to real space. Now you need a uniform distribution to add these displacements. And in literature, people generally take a uniform grid as an example of uniform distribution. So if you have a uniform grid, then you can simply add these particle displacements to the grid positions and get the positions of the particle in the perturbed universe. The velocities are calculated using this equation of motion. Basically, velocities are proportional to the displacements. Here, f is the logarithm derivative of the growth factor. So now you have the positions and velocities of the total matter. But if you want to get the positions of the dark matter and baryons separately, you have to split the total matter into dark matter and baryon. and then have to displace them with constant vectors which are anti-proportional to their masses. And the same velocities is assigned to both dark matter and baryon in that case. So this is the traditional method of generating cosmological initial conditions which are used in Laminar Forest simulations. These initial conditions are generated at early redshift, like redshift of 100, and then they are evolved with cosmological hydrodynamic simulations up to a late redshift. Here, in this plot, the y-axis shows the power difference between dark matter and baryon. I have shown two curves here. The blue curve shows the result from the linear perturbation theory, and this black curve shows the result from the traditional method of generating initial conditions I have just mentioned. So you can clearly see that the traditional method fails to reproduce the linear theory power difference in this case. And in the right plot, I have shown the dimensionless 1D flux power spectrum using the traditional method at redshift 9. The left plot is at redshift 9. I have shown this right side plot because this is one of the statistics of the Lyman-α forest, and the data are available here. So the question is how one should proceed to reproduce the linear theory power spectrum well. So it turns out that there are two modifications one has to make with respect to the traditional methods. The first one is that you have to use separate transfer functions for dark matter and baryon, and this has to be done both for particle displacements and velocities. Here I have shown the velocity equations in synchronous gauge. Here H is the synchronous gauge density perturbations, and theta B is the baryon velocity dispersion. So instead of using the Zeldovich approximation of assigning velocity, we will now use the linear perturbation theory variables directly in the initial conditions. And the second modifications is related to the uniform distribution of particle. So instead of setting everything on a grid, we have to take dark matter on a grid and glass on a baryon on a glass configuration. Now, what this glass configuration means? So glass configuration is created, you start with particles randomly distributed, uniformly randomly distributed, and then you evolve this configuration with negative gravity up to a scale when they are gravitationally stable. So these two modifications have to make in order to get the linear power difference correct. So this plot shows that we are successfully reproducing the linear theory power difference. Here, this red dash curve is the result from our new method, and this is the plot which shows the dimensional Lyman-α flux power spectrum from these two methods. So the black is the traditional, and the red dash is the new method I just described. And here the yellow band shows the data accuracy available at redshift 5 in the literature. So you can see that these two methods match quite well at large scales, I mean small k values, but the situation becomes worse as you go towards the small k values. And at a velocity scale of around 0.1, you can see that there is a approximately 75% difference between these two methods. And this is well beyond the accuracy of the data. And we check that this result remains same irrespective of the redshift of the initial conditions and also the numerical simulations. Right now, you can ignore this enhancement at small scales because this is quite numerical. This is primarily dominated by the glass noise. If you increase the numerical resolution, then this feature will go away. We have also looked in detail what the reasons behind this difference. So in this plot, I have included three more figures, three more curves. The blue curve is the case where you just replace the peculiar velocities of the new method with that of the traditional method, keeping all other quantities same in the new method. And orange is for replacing the neutral hydrogen density distributions. So for these two cases, you can see that the difference reduces to half at a velocity scale of 0.1. So, and if you combine this both two, I mean, peculiar velocity and neutral hydrogen distributions, then you end up getting the traditional result. It matches the traditional result. So the conclusion is that the peculiar velocity and neutral hydrogen distributions are the reason behind this difference between these two methods I described, and they are contributing equally. Yeah, with that, I would like to conclude. So my main message is that if you want to reproduce the linear theory power difference, that we will end up getting a 75% difference in the Lyman-α flux power spectrum with respect to the traditional methods in the literature. And this is well beyond the accuracy of the data available. And current disagreement in the dark matter mass inference I mentioned at the beginning is likely due to the difference we just discussed. And we are working on this. And lastly, our finding points are to more accurately Laminar Forest simulations. With that, I will thank.
Thanks for the talk. Questions?
When you're considering the dark matter particles and the baryonic particles to be separate species, why are you just changing the velocity initialization? They also have different transfer functions, so their displacement should also be different.
Yeah, so I have not mentioned the displacements here. So displacements
is also
transfer
different.
function is also different.
Okay.
For this place.
And then you didn't quite motivate why you need to go to glass for baryons, because you could also offset the baryonic particle, the baryonic grid from the dark matter grid. And that would, so there's the worry that the baryonic particles get stuck to the dark matter particles.
Yeah, so yeah, this particle coupling could happen, but this is the effect at these small scales.
No, but why did you go to glass is what I'm asking.
So it turns out that if you don't, so I have not plotted that to show, but if you use different combinations like glass, grid, and something like that, all the combinations, it turns out that these combinations is producing the linear theory power difference. I don't have any physical reason behind that, but.
Okay, thanks.
More question? Okay, then let's thank Nabendu and all other speakers in this session.